You ready? Let's do it. Okay, welcome back everybody. We're going to continue with this example that we were working on last time. Again, there's lots of things to think about in all these examples that we're talking about. We're working through the algebra, omitting a lot of calculus because we don't need to work out the integrating constants on things, recognizing kernels, understanding distributions, and understanding what our answers mean. So that last step is the hard part for people. Everybody thinks, oh, I just need to get the right answer on a test. But you need to understand what your answers mean and how to interpret them and understand if they're reasonable. So that's the big key. Okay, so we'll look at the solution here and talk about it for a few minutes. After we're done with this problem right here, we're going to study a new problem. We're going to study this thing right here. And when I write this down right here, I mean we're going to get rid of the phi in here, or the sigma squared. I'm going to marginalize it out. So in the first problem, this was conditional on sigma squared. We're going to get rid of that thing. So a little bit of calculus involved in that step, and I'll teach you how to omit it so you don't have to hand integrate everything. Okay, just a quick note, we'll have a review session tonight. Review at 5:30 in 207 seats. We'll go for as long as it makes sense. I've never had one under an hour. I've never had one over 3 hours. But we'll be aiming for about an hour and a half. Yes, please.
Do you tape those?
I do. So I'm going to record them. I am going to probably, I might post it in the morning. So I have a bunch of stuff to do once I get home.
Yeah.
I'll probably post this lecture on time. And then I'm going to send out a password to you guys. So I'm going to password protect the review sessions. So just because there's all the solutions to the homework, you know, that sort of thing. Also, what I would like you to do so that we can organize this is post questions to Slack. So if I show up and there's no questions on Slack, I'll assume there's no questions, I don't bring a lecture to you. And so the reason this is helpful is sometimes you guys will ask questions and I can answer them in one conversation. So the order of your questions matters. And I'll try to sculpt for you a discussion of the problem you're asking and take you as far into the solution as I think is reasonable. So I'll just say post questions to Slack. I don't know if I've created a channel on there for review session. Did I do that yet? We haven't used Slack too much. Only a couple little logistical questions have come in. You guys can let me know. I can put a channel on there. There is one. Okay. So in review session on Slack, just write your question. You know, please don't write problem 3. So, you know, I mean, it's funny, but it's ridiculous at this point. You know, I know somebody's going to do it, but just try to ask what your question is. You know, that's half of it right there. Can I articulate the question and figure out where you're stuck? I think we can do better than, I just don't even know. I have no idea. I don't even know what to do here. So if it is that, I'll answer those questions as well. It would just be better for organization's sake if you can ask specific questions on the slide. I usually check in about 10 minutes before the review session begins. So, okay. Cool. Any questions before we start up? Let me just review. We're studying this problem. We have one data point from a normal distribution. On the homeworks, you'll be cranking up n, and we'll be handling these cases where n increases. But there's interesting stuff to see, like where does one data point get you? How much information is it compared to the prior? And we'll see what the impact of n is later. So studying one data point from a normal distribution, our goal is to find the posterior distribution, and I reparameterized it in terms of the precision instead of the variance. And the only reason I did this is because the form of the likelihood, if I parameterize it in terms of the precision, it's gamma. And so the conjugate prior is gamma. And if you think that's not a good enough reason to do it, I really like working with sigma squared. That's the parameter I understand. And I'll let you know, you don't understand sigma squared. You know, there's nothing you get about it, this smooth function. You understand the mean and stuff like that. That's like human capability. I understand squared residuals, squared differences from the average, some of those things, you know, you kind of understand it. It feels natural to you because you've been working with it for a long time. It does fall out of normal distributions. It's a parameter that's in there, but it's arbitrarily encoded. I could flip it upside down. So you could have gotten used to precision a long time ago. In this class, I'll be playing around with precision just because I like gamma distributions and I don't like dealing with inverse gamma distributions. But if you like working with inverse gamma distributions and you decide to do all your homework that way, and you do your midterm that way and your final, you write all your papers that way, no problem. So you can do it that way if you want. Okay, some people work with not sigma squared, and they work with sigma. It's the same sort of thing. They're all one-to-one with each other. So all the same information. If you liked sigma squared, you could take your answer at the end of the day and do a transformation of variables and just invert this parameter and transform that thing. Again, it's a one-to-one thing. You can work that out and it'll be on an inverse gamma scale. And so you give somebody one answer, they want it on a different scale. If it's a bijection one-to-one, it's just a transformation of variables. Okay, so this is where we were last time. I apologize. I had flipped those around at the end of lecture. I had accidentally wrote BQ, but we were doing inference on fees. So if you noticed that in your notes, and I wrote it down wrong, you're right. So this is what we should have written down. We wrote down the equations correctly. So our posterior distribution, this is Bayes vanilla. It's just likelihood times prior. We're all in the doing parametric analysis, and we're working with a conjugate prior. Conjugate prior is gamma, since I've re-encoded everything to the precision scale. I like thinking about precisions just as much as I like thinking about variances. So it means the same thing to me. Okay, so you know what this is? So we'll just write it down. So we've written down a likelihood. This is phi to the 1/2. I've omitted my square root 2 pi. E to the minus phi x ops minus mu squared over 2. And then I've got my prior right here. And I'm writing down the normalizing constant to get you used to it. In the next problem, we're going to need to know what it is. So we're going to need to know this form right here. We'll look at it a little bit later. For this problem, we don't need it. So this is going to look like phi hyperparameter alpha 0 minus 1 e to the minus phi beta 0. And as we've said already, this thing's conjugate. This thing will multiply through and it will preserve the form of the gamma kernel. So this looks like phi to the 1/2 plus alpha naught minus 1. So this minus 1 that I get from the conjugate prior, I never absorb it anywhere because I like it written down with the minus 1 so I can recognize what the important piece of information is, this thing. That's one of your parameters that dictates what the gamma looks like. E to the minus phi, x obs minus mu squared over 2 plus beta naught. Have those in braces. And so I recognize what distribution this is. So if I ask you on a midterm or in a homework To work out the posterior, what I'm asking you to do is tell me which distribution it is and tell me all its underlying parameters. So if you just tell me it's a gamma, you haven't told me which gamma, that's not an inference yet. So if you tell me just what the parameters are and you don't recognize the distribution, which it would be impossible to do. So I would know you have to know what the distribution is, but you got to say what it is. So you would say this is a gamma with these two parameters, 1/2 plus alpha naught, x obs minus mu. You get to know what mu is in this problem divided by 2 plus beta naught. And that's my answer. So this is the posterior distribution. So let's think about this answer for a minute. First thing I usually like to do, because I guess I trick myself into understanding, to telling myself that I understand means. I understand them when everything is symmetric really well, but when they're skewed, I'm like, eh. And this is a skewed distribution. So, you know, I know that the mean's probably somewhere in the mass of this thing, maybe floating down the tail, but it's probably around the bulk of this distribution. That's not always true. Means can live in low mass areas of distributions, multimodal distributions. The mean would be a very poor characterization of what's going on. But for this problem, maybe the mean is something that I can think about for a second. It's on a relatively human scale, so I like to think about it. So let's just think about what the posterior mean is. See if we're comfortable with this answer on any level. So I want this thing. Expectation phi given x and mu. It's a conditional answer. How do I work this thing out? It's just the integral of phi times the posterior. I can work through this. This goes from 0 to infinity. I know what the posterior looks like. I can encode the whole thing. Usually I don't do this, but I'll write it down here. This is going to be, I'm going to give these some names. I'm going to call this alpha twiddle, and I'm going to call this whole thing right here beta twiddle. Just to shorthand my notation a little bit. So this is going to look like beta twiddle to the alpha twiddle over gamma alpha twiddle. This looks like phi to the alpha twiddle minus 1. Just the same thing that we wrote down, but I'm throwing in the normalizing constant. E to the minus phi beta twiddle. So I could do this integral. I could work through everything. How would you do it? I think you would have to start understanding properties of what a gamma distribution looks like, soak that thing in, figure out what's integrating to a 1, and factorize everything else out. That's how I'd go about business. I'd have to understand what the gamma distribution looks like. I'd have to understand what the normalizing constants are, so on and so forth. I don't feel like doing it. Does anybody know what the answer is off the top of their head? That's it. Alpha twiddle over beta. Searing didn't think about all of that. She knows she's worked this problem out once upon a time. She can convince herself she knows how to do this integral, but she knows what the expectation of a gamma is. And that's kind of one of the beauties of a conjugate analysis is if I know the properties of my prior, then I know the properties of my posterior. It's just updating everything using the data. So now the data is involved in this. So that's the expectation. Alpha twiddle over beta twiddle. And then I just write this down. What is alpha twiddle? it's 1/2 plus alpha naught over x obs minus mu squared over 2 plus beta naught. Okay, so that's our answer, and maybe that makes some sense. Let me just ask some questions. See what you know about variance analyses. So quick question. What's the MLE, the maximum likelihood estimate, for sigma squared? And maybe you write this down as sigma hat squared MLE. Maybe you know what it is. So what is it? It's when I take the likelihood, that is this part of everything, and I maximize it. How do we do this? Take a derivative, set it equal to 0. Warren's like, ooh, if I tried to do that on a qualifying exam, that would sure waste an hour and a half. Take the logarithm first. Make your life a lot easier. Linearize that thing. And take a derivative, set it equal to 0, and find the answer. And some of you are pros at this. What's the answer? Sum of the xi's minus mu squared over n. Right. So it looked like this in general. So xi's minus mu squared over n. I goes from 1 to n. N is 1 in our case, but I'm glad that you said that. And you divide it by the right number n in all of this. And that's what the answer is. So let me just ask a different question real quickly. So this is something that you would learn in, Stat 101, I think they hand you this. They just hand it to you. Once you take a grad or a higher level undergrad class, they have you work that thing out. And this is what you work out by maximizing the likelihood. So a pretty trivial calculus problem for a graduate student. So here's another question. What's the MLE for sigma squared, or for phi? So I'll write that thing down as phi hat MLE. And if I give you the MLE to one thing, you can probably figure out the MLE for the other one. Nice theorem in inference that says they're transform invariant.
Should it just be 1 over?
Yeah, it's just 1 over. This is a really neat thing that happens with maximums of functions. So you can just flip the thing back over. That's kind of cool. You cannot do this with a posterior estimate, a map, because it's a probability measure. But for a likelihood function, you can do this. So this conversation we were having a little bit, and we'll probably keep coming back to this conversation, posterior involves the Jacobian term when you transform. You have to be aware of that. So maximum a posteriori estimates and MLEs are different from the Jacobian term in the prior that's involved. So with this thing, it's just going to be the inverse of this. Xi minus mu squared over n invert. Okay, so our answer for our actual problem, because n is 1, there's no sum. This just looks like the invert of this. X minus mu squared. So I do like to think about other branches of statistics. What inferences would they come up with? How does it compare? Could I have both things simultaneously? Maybe I could appease my classical friends with a Bayesian analysis. I could still give the interpretation of everything. It's a belief interval that I can construct. I have a probability measure. on everything that I want to compute. So I get that interpretation out of Bayes, but I could align my answers. I'm not saying you need to do that. I'm just saying it's a possibility. So this answer might look a lot like that answer. And this is an x-obs, or one observation. So what would alpha 0 and beta 0 need to be?
0.
0. Now, I'm not saying that this is correct thinking, that it's like I'm going to justify my hyperparameter choice based off of some classical rationale. There's something weird there. But I'm not going to say that you're not allowed to think about it. So if alpha 0 is equal to beta 0, and this is a good choice, I'll just point out, this is the reference prior, it is the Jeffreys prior, there's lots of other good reasons for picking these choices, but right now we're just using our intuition. If alpha 0 and beta 0 are equal to 0, then expectation of phi given my data, and my data is just x-obs in this case, and mu, this is going to be equal to phi hat MLE. You can work that out. I'm not going to ask you to work out MLEs on a test or anything like that. This is a Bayes class, but we do like to discuss other things. This would just look like 1 over x obs minus mu squared. So you get the same answer back. If you wanted to use the mean and match it to a MLE, something off about that just on its own, but I will give you other reasons for picking this choice later on. So wait till Jeffreys prior. We'll come up with this exact same thing. So this is the transform invariant choice as well. That has a lot of appeal. Again, it's about a month down the line. So right now we're kind of left with an unsatisfactory understanding of why we picked those choices, but it feels good. So I've got a point estimator that maybe I like for other reasons. And I have a probabilistic interpretation of where I think that parameter lives. I guess that's good. I like both those things, nothing wrong with those things. So this is maybe a good answer. So maybe we like this answer. I do like this answer. Just to let you know, I think it's all right. It's probably what I would hand somebody if they asked me the precision and say you have one data point and you know the mean. Okay, I guess maybe this is what you think. And I could give you a pretty wide interval. So if we studied the gamma distribution that we ended up getting with alpha tilde and beta tilde, the intervals you would form would be pretty wide because there's not a lot of information going in there. And so I probably wouldn't do the analysis. I'd probably say go get some more data. But I think the answer at least makes some sense. Note the implied prior. Let's just write this down. This looks like this. V to the alpha 0 minus 1. E to the minus phi beta 0. These things are zeros. That's a 0. That's a 0. So this thing becomes 1. Don't try to compute that normalizing constant. You will have trouble. This is just going to look like 1 over phi. That's my prior. This is improper. Remember what this thing does. Integral. Put it a little higher. to infinity, 1 over phi dphi. I should probably take a limit and make my math teacher happy with me, but I'm not going to. This thing diverges. Yeah, when you add all these little things up on a continuous spectrum, they're getting small, but they don't get small fast enough. And so in your first calculus class, you've studied divergent sums. The integral of this thing is the natural logarithm. When you try to evaluate the natural logarithm, it blows up, so it diverges. So can't do that. I.e., this thing goes to infinity, so it's improper. And maybe we like that. We didn't concentrate mass too much anywhere. We put a lot of mass down in the tail. And this prior right here is kind of saying maybe you think that you prefer smaller values of the precision, larger values of the variance. So a priori, you think the variance is pretty high. And only the data is going to change your mind. And that's what Bayes does. Is you start out with this belief. This, I would say, are weak beliefs about phi, just because there's so much mass everywhere. The other's a little bit more tucked over. So 1 over phi tucked over by the origin. This thing looks like this. It's certainly not flat. So that's one key point, is that the prior we used for our normal mean was flat. And the prior that we used for our phi is not flat. And the nature of these parameters is entirely different. One is bounded. It has a hard boundary right here. So we see a penalization on the boundary. And so this is regularizing that boundary. I will point out, Laplace, a lot of people think that Laplace just played around with the uniform prior. And he was doing what Fisher was doing 100+ years later. Laplace used this prior as well. He also advocated this. I don't know how he came up with it. It's still a mystery to me. But in one of his writings, he uses this thing. So he had some key insight. And of course, all these gurus back in the day, their margins weren't big enough in their book, so they didn't tell us. You guys are math majors, you'll know where that comes from. So they don't always articulate everything. And having a conversation way back then was impossible. You know, you couldn't just jump on Slack. You'd have to go somewhere. So let's just think about these priors that we've come up with. So for this inference, pi mu given, and I don't care the way you do it, x obs, I could either encode sigma squared or I could use v. Do it either way, throw that thing in, either way, you'll come up with the exact same answer. So my pi mu, this thing, for this thing, our prior, our improper prior, this was pi mu, was proportional to 1, gave us our posterior distribution, pi mu. I'll write it like this, just to change the notation a little bit. Mu given x obs and sigma squared if you want. Bless you. Normal. This was centered at x obs. Good choice. And this had variance sigma squared. If I wanted to parameterize it in terms of the precision, I can write it down by flipping over all my sigma squareds. And so we kind of like this answer. And for this problem, right here, we came up with something different. So our two improper priors look different. And they should. But let me give you some intuition. And I'm not saying this is what Laplace was thinking about, but I always suspected. So mu is a location parameter. scale parameter. So what I mean, you guys that have all had a stats class before, if I take a random variable and I add some value to it, it will shift that random variable around. Mu is acting the exact same way. So if I move mu by 5 units, it will shift the distribution by 5 units. And it doesn't mess with the scale. So that's an additive shift. So it's an additive parameter. I.e. it's a linear shift. And I've got no problem with that. So B's totally different. B's a scaling parameter. So think about if you take a random variable and you multiply it by a number. Where would that get soaked up in the normal analysis? It gets soaked up in the scale. So if I multiply a normal random variable by a number c, let's just say, then the variance increases by c squared. So it comes in as a squared on there. So it multiplies the sigma, is what it's really doing. And certainly you guys have worked through that before. So this is a scale parameter, i.e. it's a multiplicative parameter. So if I multiply a random variable by something, I don't change the shift. I don't change where it's centered, I change its diffusion. If I multiply, or did I just said that. If I add, I don't change the diffusion. I just slide that distribution around. I'm not changing how diffuse that distribution is, just sliding it. And so this has an obvious additive interpretation, and this has a multiplicative interpretation. And if you know much about scale location families, you kind of know how to reparameterize them in one step. And what you always see that jumps out in front of the distribution is the rescaling of the parameter. And inside the argument, you see the shift and the rescale. So this is a little theoretical, but I'm going to water it down a little bit. Let's just talk about this real quick. So because this is a location parameter, we probably want to induce a prior that's invariant to linear shifts. So for mu, it's a linear shift. We might not want our prior to put info in about the shift. So I don't want my prior to add a lot of information as to where this thing is centered. Why? Because that's what I'm trying to infer. And I don't want it to be completely dictated by the prior. So the math way of saying this is we want a location invariant prior. Every time I see the word invariant, I think, invariant to what? It means I'm going to change something, but I want something else not to be affected by it. So that's what I mean to be, it's invariant. It can't be invariant to everything. I include information in some way, but I don't want to include it in certain ways. In this case, I don't want to say a lot about where this thing is located. So There's only one distribution in the world that can do that. So again, we're thinking about mu on mu scale, not mu squared scale, not 1 over mu scale. Thinking about the nature of mu itself. And I'm interpreting it on this scale. And so there's only one distribution that I can slide back and forth, and it doesn't change the distribution. There's only one that I can think of. If I take that distribution and I slide it back and forth, and I can't tell, what is that distribution? It's the infinite uniform. So the uniform that goes all the way that way, all the way this way. If I slide that line, it looks the same. You can't tell. If you're a uniform 0, 1, you'd be able to tell. And so this right here is invariant to linear shifts. So one way you can think about this is I can just think about the anti-property of everything. I can take 2 points on mu. I'll say mu1 and mu2. These are just 2 points in my space. I'm going to add some constant shift to it, and I'm going to subtract the difference between these two things. And this is equal to mu1 minus mu2. You don't need to think too much about this. I'm trying to teach you what Haar invariance is. And so Haar invariance is invariance due to locations and scales. So the way you check to see if something is Haar invariant is you take whatever the operator is, in this case it's addition, you add those things in and you subtract, and you see if it's the exact same thing. I've said the same thing in lots of different ways. This is a more technical way of thinking about it. This is harder for me to think about, this parameter. But the same thing happens. It's a multiplicative parameter. And so if I think about 2 points on V space, V1, V2, I multiply by C because it's a multiplicative parameter. And I do the same thing to anti-property. This is V1 and V2. It's invariant to that rescaling. Invariant in what sense? On a multiplicative scale, because it's a scale parameter. So how do we rescale things? We multiply or divide. So what that's supposed to tell you, I'm not going to really test you hard on this, is that these improper priors make sense. So the additive one, the infinite uniform, is invariant to linear shift. This prior right here is invariant to scales, 1 over phi. I'll say proportional to 1 over phi is invariant to scale changes. Do you know your forms of your location scale families? You'll know that that 1 over sigma always pops out. If you transform this to sigma, it would be 1 over sigma. So I'll just say a few things. These are transform problems. This is equivalent to if I had stuck my prior on sigma squared, you can work through the transformation. This would end up being proportional to 1 over sigma squared. How do I do that? Everywhere I see a phi right here, I plug in 1 over sigma squared, flip that thing upside down. I'm not done yet. I need the Jacobian term that I multiply by. When you do that, you will get this. You should work on that. For sigma, it's proportional to 1 over sigma. You can work on that. So if I parameterize everything in terms of sigma squared, if I like this prior, I would like that one. If I changed everything to sigma, I would like that prior. It's just the transform. These are all 1 to 1 with each other. Just have to do your transformation of variable form. If that's confusing, just transform the variable. That's it. All one-to-one. So that's invariant to scales, where our flat prior on mu is invariant to linear shifts. Do I care? If it's a linear shift parameter, I care. So if I applied a flat prior to sigma, I'd be saying I want my precision parameter to be invariant to linear shifts. And it doesn't make any sense. It doesn't have that interpretation, so it's not something you would desire. If you don't like any of that, that's fine. I'll give you other reasons for liking these priors later on. So I think maybe Laplace was trying to come up with something he knew about location scale parameters. He actually used this prior right here, but it is equivalent. So I think he was just trying to come up with something that was invariant to scale. He doesn't say that. Or at least when I read through these things, I don't read that, but I can't quite read what they say. So I need another PhD to be able to do that. Okay. Good for now? We'll keep coming back to this. See lots of reasons for liking things, but I think it's starting to pile up. But it's like, I've got 2 or 3 good reasons for liking these priors. They're definitely not probability distributions, those priors, because they're improper. But the posteriors were proper. So, still have a lot. Let's study another problem. We won't finish this, but let's just do one more. So, one more example. I'm going to ask you to do the other one, I think, on the next homework. But let's come up with this distribution. Find pi mu x odds. Now here's where the notation gets tricky. It's like, what do I mean by this? Do I mean I'm conditioning on sigma squared? I don't mean that. I mean sigma squared is out of my equation, or phi's out of the equation, depending on how you parameterize it. I like to work with phi because I like m. So how do we find this? There's only one gig in town. There's nothing else you can do. How do I find that distribution? Bayes. 2 Bayes. So Bayes is the thing that flipped it over. And then what? I just apply Bayes. How do you get rid of a parameter in a probability distribution? You integrate it out. You average it over. You average over it. You marginalize it. So you marginalize. So average, integrate, marginalize, all the same thing. So Bayes is correct. You find the joint distribution, find mu, phi, given x odds. Find the joint. Once it's a probability measure, you have the luxury of averaging over it. So integrate over phi. 0 to infinity. That's how you do that. Every single time. What does it mean? You're saying what mu is on average. So you average over the whole distribution. So it's an averaging process. I like that. Bayesians are allowed to do that. So I average over all the uncertainty in phi. I already like that. So that feels really good to me. What distribution do you think this has? Just any guesses? What would you guess? T? And maybe a T. So Stephen's thinking in classical stats, when I don't know sigma, I use a T distribution. When I know sigma, I use a Z distribution, the normal distribution. So maybe a T. And in general, that's true. So a little bit of insight, maybe a T. Let's see. I will have to tell you about t-distributions, and that's coming next time, so it'd be good if you looked them up and saw what the parametric form of a t is, so that it's not any huge surprise to you. But let's just work through this thing real quick. Gotta integrate. So I'm gonna just launch through this thing. I'm gonna say this is proportional to, I'm too lazy to work out all my integrating constants and figure out exactly what this is. Let me just ask, what distribution is this joint? It's like, it's normal in that condition on mu given phi, it's gamma over here. What is it? It's something that kind of looks gamma and kind of looks mu, depending on which margin I'm looking at. So one looks normal, one looks gamma. So that's called the normal gamma. In general. So something you don't know that much about. So the Bayesian is going to think about the interaction between these parameters, how they influence each other, and they certainly do. You cannot factorize them away from each other. So this is just going to be proportional to the likelihood of phi and mu, given my data point, times my prior. Now I took my priors to be conditionally independent. There are ways that you can build dependence if you knew it, but I'm implying that my prior beliefs on everything are conditionally independent. And I'm going to integrate over phi. Which priors am I going to choose? Maybe I'm hopeful that our priors that we came up with before, I can use them here. So maybe 1 is this prior, proportional to, and this one is 1 over phi. There's other choices you could make, but we liked these before. Had success with these. So it certainly makes the calculation pretty easy. So likelihood times prior is proportional to the posterior. Everything down to the denominator doesn't have anything to do with mu or phi. So maybe I can just recognize what the kernel of this distribution is after I march through the integral. So this looks like this. This is going to be phi 1/2 e to the minus phi x obs minus mu squared over 2 times 1 times 1 over phi. So sometimes you'll see people write the joint prior for mu and phi is 1 over phi, and mu doesn't appear because it's flat. This isn't too hard to deal with. There's my minus 1 right there, so I'm just going to clean this up. Minus 1, and I'm integrating between 0 and infinity. And if you knew how to do that first integral for finding expectation, this is the same sort of thing. You would know how to do this integral. Does anybody know what the answer to this is? What does this look like? It looks like a gamma. Which gamma? The 1/2 and this stuff right here. So this looks like a gamma. 1/2 x obs minus mu squared over 2. If this had the normalizing constant for that in front of it, it would integrate to 1. So if I have my normalizer, what does this look like? This is the inverse of the normalizer. And so this is just going to look like gamma to the 1/2. That's just gamma function 1/2. That's a neat number if you don't know what it is. Over x obs minus mu squared over 2 to the 1/2. So this is the alpha to the, this is the beta to the alpha. This is gamma alpha. So you kind of need to know what that gamma form looks like. I'm going to rewrite that, and then I'm going to let us go. But this is proportional to 1 over, I can get rid of the 2. That thing doesn't matter. I've already written this answer up to proportionality, so I can just chuck the constants. The only thing that depends on mu in the data is this chunk. So this is going to look like x obs minus mu squared to the half power. That's equal to 1 over x obs minus mu absolute. Jenny?
Okay, so where did 1 over phi go?
Louder, please.
1 over phi. Where did we take that? Because I don't see it in that final expression.
Let me answer your question after class.
Okay.
I'm just going to conclude and we'll come next time. If you guys want to crowd around the board and see whatever step it is you're talking about, that's fine. Just one question, 10 more seconds. Anybody like this answer? Or do you hate it?
It's not continuous.
It is continuous. So, but it does have a sharp point.
Yes.
So it has a sharp point right there. So maybe you don't like the sharp point, but I don't think that's a huge problem. Any other problems? It's not proper. If I integrate it over this with respect to mu, this is a distribution on mu, it's divergent. I want us to come back next time and think about that for a minute and figure out what should we do. Let's come back next time and answer that question. Thanks, you guys. Yeah. Whatever what? Oh, whatever. Yeah. Yeah. It's in here. I had it here, and I have it right
What?